All right, so this is going to be our walkthrough for the assignment titled More Optimization and Related Rates. So we're going to have some optimization, some related rate problems. They may be kind of mixed together, so you're going to have to determine what's what. So it should be pretty obvious. If you read this one, if you just read the last sentence, find the dimensions of the page that will allow the largest printed area. So that's going to be, we're looking for a maximum area, which means this is an optimization problem. So we have a page of a book that needs to have an area of 90 square inches. So here is a page of a book, and its area of the entire page needs to be 90, right? And that's going to just be whatever this x value is times whatever this y value is, right? But what it then says is it's got 1-inch margins at the bottom and the sides, and a 1/2 inch margin at the top. So the printed text actually looks more like this, right? Where this is 1 inch, this is 1 inch, this is 1 inch, and this little bit here is 1/2 of an inch. And so the area, and we'll call it the area of the text, maybe a sub t. You can use whatever variable you want, but the area of the text is going to be a little bit different. It's going to be x minus 2 because my full length here is x and I'm subtracting 1 on each side, and then times y minus, well, the y value, right, is the whole thing, so I'm subtracting 1 1/2, so I'm going to subtract 1.5 or 3/2. So the area of the text, which is what I want to maximize, like the area of the printed text, we can find that by just multiplying these two things together. But first, we're going to want to rewrite this in terms of either x or y. So we know that if 90 is equal to xy, then y is equal to 90 over x. So we can go in and we can replace this and say the area of the text is x minus 2 times 90 over x minus 3/2. Then we'll distribute all of that out, right? Which is going to give us the area of the text is going to be, well, x times 90 over x is 90. X times negative 3/2 is negative 3/2 x. Negative 2 times 90 over x is negative 180 x to the negative 1. Right? And then negative 2 times negative 3/2 is a positive 3. So the area of our text space is now going to be 93 minus 3/2 x minus 180 x to the negative 1. And we should then be able to figure out what a prime of our text area is. Right? A prime sub t is going to be, well, the 93 is a constant, it'll go away. So we'll just have negative 3/2 plus 180 x to the negative 2, or 180 over x squared. So what we'll want to do is we'll want to get a common denominator for this, which means I'm going to multiply by x squared over x squared there, and I'm going to multiply by 2 over 2 right there to give me a common denominator of 2x squared. So we end up with negative 3x squared plus 360 over 2x squared. And of course, we want to look for when this is equal to 0 and when it's undefined, but when it's undefined is when x is 0, which doesn't give us a page of the book, so that makes no sense. So we'll set it equal to 0. We'll do that on the next page. When we do that, we have negative 3x squared plus 360 needs to equal 0, because if the numerator of it equals 0, the whole thing does. So that'll just give us x squared is equal to 120, or x is positive or negative, and we'll simplify root 120. That's 4 times 30, so that'll be plus or minus 2 root 30. And of course, only a positive length for a page makes any sense, so we'll say only 2 root 30 makes sense here. And then we need to prove that this is actually when we have a maximum. So in order to do that, we'll make a sign chart, putting 0 and 2 root 30 on it. Right? And if we plug that into our derivative, well, if we look at our original derivative, we know that the denominator of it was always positive. So really all that matters is the numerator. So if I put in a really big number like, 10 billion, right, that's going to make the numerator negative. But if I put in something small, like let's say 1, that's going to make the derivative positive. So we're going to go from positive to negative derivative, which means that this area, a sub t, is going from increasing to decreasing, which means we are at a maximum when x is equal to 2 root 30 inches. And I believe the question asked for the dimensions, which means we also need y. Well, luckily y is just 90 over x, which would be 90 over 2 root 30, which would just be 45 over root 30 inches. And so that's our first problem. So for our next one here, we've got a right triangle. So I'm going to draw a right triangle right off the bat. Right triangle with a hypotenuse that is root 3. And what we're doing is we're revolving it around one of its legs to generate a right circular cone. Right? And so we want to find the radius, the height, and the volume of the cone of greatest volume that can be made. So we've got a height and we've got a radius. And it doesn't really matter which leg we're revolving it around for this problem. But what we do need to recognize is that our volume for a cone is always going to be 1/3 pi r squared times h. And so what we need to do is we need to solve this for one of our two different variables, right? Either for r or h in some way using this right triangle. Well, we know that r squared plus h squared ought to equal root 3 squared. And so it actually looks like the easiest way to do this is to go ahead and solve for r squared, right? If r squared is just equal to 3 minus h squared. So our volume should be 1/3 of pi times 3 minus h squared times h, okay? Which is just going to give us volume is 1/3 of pi times 3h minus h cubed. And we should then be able to take our derivative here, remembering that, not dv dt, which is v prime. We're looking for a max, so this is an optimization problem. So v prime here is going to equal that constant, 1/3 pi, times 3 minus 3h squared. And when we do that, we just set this equal to 0, which gives us, well, the 1/3 pi doesn't affect it. It's just 3 minus 3h squared equals 0, which gives us h equals plus or minus 1. So obviously a height of -1 doesn't make any sense, so only a height of 1 makes any sense here. We do want to prove that this is a maximum when the height is 1 meter. Right, this is 1 meter, so we'll indicate those units here. We can do that with a second derivative test. That'd probably be easier here than making a sign chart this time. Right, so our second derivative, v double prime, is still a 1/3 pi. Right? And then it's times the derivative of 3 is 0, and the derivative of negative 3h squared is negative 6h. And so if I evaluate that at 1, we clearly get a negative number, which means it's concave down, which tells us the function looks like this, which means it's a maximum. So we do have a max when h is 1. We also need to figure out what the radius is and what the actual volume is. So our radius, well, this is an r squared over there. Our radius, we should be able to find by just solving this other equation, right? R squared plus h squared equals 3 tells us that r squared plus h squared, so r squared plus 1 equals 3, or r squared is 2. Well, we're going to get plus or minus 2, but really it's just going to be root 2 meters because we're not going to have a negative there. And then to find the actual volume, well, the volume itself, right, is going to be 1/3 of pi times the radius squared, which is 2, times our height, which was 1, which is 2 pi over 3 meters cubed. So for our next one here, we've got sand falling from a conveyor belt at a rate of 20 cubic meters per minute, and it's making a cone. So first of all, we'll do volume is 1/3 pi r squared h. And we also know that the rate of change of the volume is 20 cubic meters per minute. We're told that the height is 3/8 of the diameter. Right? Well, if the height is 3/8 of the diameter, well, diameter is 2 times the radius, so that'd be 3/8 of 2 times the radius, which would mean that the height is 3/4 of the radius. So we're probably gonna need that here in just a minute. When we plug this all in, we're going to recognize that the question's asking about when the height of the pile is 4 meters, right? And we want to know how fast the height is changing, so dh dt. So we probably want to put everything in terms of h, since we're given an h and we're asked about, actually the height of 4 meters. Then we're also asked about the radius changing, but we'll deal with that afterwards. So it's probably easier to do the rate of change of the height first. So we'll go about it that way, which means we need to actually solve this for r, right? R is going to be 4/3 of h. So what we'll do is we'll plug that in. Volume is now going to be 1/3 pi times 4/3 h squared times h. And when we simplify that out a little bit, it looks like it becomes 16 pi h cubed over 27. And so as we take our derivative with respect to time, we're going to get 3 times 16 over 27, which is just going to be 16 over 9. So 16 pi over 9 h squared dh dt. We have dv dt, and we have h, so we'll just plug those in. 20 is equal to 16 pi over 9 times our 4 squared times our dh dt. And so we'll do a little bit of arithmetic there. We'll multiply by the 9. So we'll get dh dt is equal to 20 times 9 is 180. And then we're going to divide by 16 times 16 times pi, which will be 256 pi. Those are both, looks like those are both divisible by 4. So that'll be 45 over 64 pi, and it's meters per minute. That's the rate of change of our height of the pile. That's not divisible by anything. Again, we can't reduce that anymore. Now, it also asks us to find dr dt. Well, dr dt, we can just really easily find. We know that the radius is 4/3 of the height, which means that dr dt is just 4/3 of dh dt, right? We don't have to do a whole bunch more work. We just need to say that dr dt is 4/3 of what we just found, which is 45 over 64 pi. We can reduce the 45 over 3 to a 15, and the 4 over the 64 to a 16 in the denominator. So we've got 15 over 16 pi meters per minute. So you don't need to reinvent the whole wheel there. Just use this nice little relationship you have between h and r to find the rate of change of the radius once you have the rate of change of the height. For our next one here, we have a balloon that is rising vertically above a level, straight road. All right. As that's happening, we've got a bicycle that is moving at a constant rate of 17 feet per second, passes under it, right, at the exact moment when the balloon is 65 feet above the ground. We want to know how fast is the distance between them increasing 3 seconds later. So this one It kind of sounds like it's going to be complicated, but it's really not all that bad. So what we've got here is we've kind of got a right triangle going on. Right? The balloon is rising vertically. We'll call that y. We've got this distance between them, which is z, and then the distance that the bicycle is away from that liftoff point of the balloon, which is x. Right? And so we can obviously come up with a relationship here that x squared plus y squared equals z squared. Or in other words, right, we've got 2x dx dt, if we take the derivative, plus 2y dy dt is equal to 2z dz dt. And of course, the 2's can all cancel. So we really just have x dx dt plus y dy dt equals z dz dt. We just need to figure out what each of those things are. And we're actually kind of given all of these things, almost all of these things right off the bat. Right? The balloon is rising at 1 foot per second. So if it's rising at 1 foot per second, and it's already 65 feet above the ground, right? Well, this height of y is just going to be 65 plus the 1 foot per second times the 3 seconds later that we're interested in. So y is just going to be 68. So we're going to have a 68 here for y. Dy dt we're given, right? It's rising at 1 foot per second. So we've got that. The bicycle is moving at a constant rate of 17 feet per second. So dx dt is just going to be 17. And then the distance that the bicycle moves, right, in those 3 seconds is just 17 times 3, which is 51. And then the z value, well, we need to find the z value. That's the only one we're not given, other than the dz dt that we're looking for. And we can find z by just using the Pythagorean theorem, right? Z squared should equal 51 squared plus 68 squared, right? And you know, if you go through and you do the arithmetic on that, you end up getting z is equal to 85. So I'm not going to bother with the arithmetic there. I'm just going to say that's 85 times dz dt. So we have 51 times 17 plus 68 times 1, and we're going to divide that by 85. Again, I'm not going to do all the arithmetic by hand here. You can add those up and divide by 85. You end up getting dz dt is equal to 11 feet per second. So the distance between the balloon and the bicycle is changing at 11 feet per second. All right, here we've got a 13-foot ladder leaning against the side of the house, and the base of it starts to slide away. So by the time that base is 12 feet from the house, it's moving at 5 feet per second. So let's draw a picture. Right, we've got a 13-foot ladder that's leaning against the side of the house. The length of the ladder is not changing, so I'm just going to call it 13. Right, we've got a right triangle, we've got an x, and we've got a y. We want to know how fast is the top of the ladder sliding down the wall. So that's a rate of change of dy dt, right? And so when we do this, we are going to end up using the Pythagorean theorem, right? Because that's kind of what we've got here is a Pythagorean theorem problem. We got x squared plus y squared is equal to 13 squared, or 169. And the base, we know, is moving at a rate of dx dt, which is 5 feet per second. And that x distance is increasing, so it's a positive 5. And our y value should end up being a negative in the end because the distance of y is decreasing. And the base, when we're interested, is 12 feet away from the house. So we're interested in when x is 12, which, in fact, we should know that if x is 12, what's the y value going to be? Well, it's just going to be 5, right? That's a Pythagorean theorem. A Pythagorean triple, right? 5 squared plus 12 squared equals 13 squared, right? So we should know that x is 12, y is 5, and now we can just take our derivative. 2x dx dt plus 2y dy dt is just equal to 0 because the derivative of 169, that's a constant, it's just 0. We can eliminate the 2's just like we did in the last problem. And if we're looking for dy dt, right, we just solve and plug everything in and solve. X is 12, dx dt is 5, y is 5, and we're looking for dy dt. Well, dy dt should just be negative 60 over 5, which is negative 12 feet per second. I guess we didn't need to circle the unsimplified version. Just circle that. So our next question here is actually a second part to this question. It says, at what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at that moment? So we've got the same picture as before, right? But now, right, we've got, this was 13, this was x, and this was y. But now we're looking for the area, right? So the area of this is just 1/2 the base times the height, 1/2 x times y. So we can just go right through and immediately take our derivative of this, right? dA dt should be equal to 1/2 of x dy dt plus y dx dt. Right, we'll just do this implicitly. Since we already know what dx dt, dy dt, x, and y all we have to do is just plug those values in. So dA dt should be equal to 1/2 of our x value. Well, our x value previously was 12, and our dx dt was 5. So, well, we got our x value was 12. Our dy dt that we just found was negative 12. Our y value was 5, and our dx dt was also 5. And so what we end up with here is negative 144 plus 25, which is negative 119, and then times 1/2. And since this is area, it's feet squared per second. And once again, we've now got the same problem here, but now we're asked about at what rate is the angle between the ladder and the ground changing at that moment. So a little bit different. We've now got some angle theta in here. And there's, of course, multiple ways we could set this up. It doesn't really matter what method you use. We could really use any of the trig functions that we want. But we're just looking for the rate at which that angle is changing. So, in fact, maybe we'll do this a couple of different ways. One, we'll just use sine of theta. Right? The sine of theta ought to be y over 13, opposite over hypotenuse, right? And so if I do that, I get cosine theta, d theta dt, is equal to our y 1/13 of dy dt. And so then we have to look at what the cosine of theta is. Well, the cosine of theta is adjacent over hypotenuse. Well, our x value was equal to 12 previously. So the cosine of theta is going to be 12 over 13 adjacent over hypotenuse. So 12/13 d theta dt is equal to 1/13 of dy dt. And previously we found that dy dt was negative 12. Well, we can just multiply by 13 and divide by 12, and we get d theta dt is equal to negative 1 radian per second. And we could see that if we did this, let's say, using cosine of theta instead of sine of theta, we have cosine theta is equal to x over 13, or negative sine theta d theta dt is equal to 1/13 dx dt. And when we plugged in our values, the sine of theta would now just be y over 13, right? And we knew that the y value previously was 5, so that'll be negative 5 over 13 d theta dt is equal to dx dt, which we were originally given as 5. So 5/13. If we cross multiply there, or multiply by the 13, divide by the -5, we get the same exact thing. D theta dt is equal to -1 radian per second. And I think in the answer key I posted, I think I actually did it using tangent, and you'll see that you get the exact same thing. Doesn't matter which trig function you use, you're going to end up getting -1 radian per second because that's how fast that angle is changing. So you don't need to do it twice, just do one or the other, or do a tangent like I did in the answer key, I think. All right, we got a couple more here. So this one, we've got a water tank that has the shape of an inverted right circular cone with a height of 12 feet and a radius that's base is 6 feet. We're pumping water into the tank at 10 gallons per minute. And we want to approximate the rate at which the water level is rising when the water is 3 feet deep. So we'll draw an inverted cone. So here's my cone. It looks pretty decent there. It's got a height of 12. And it's got a radius of 6. But of course, the water is being pumped into this tank. So the water level is rising up through here. And we are approximating the rate at which the water level is rising when the water is 3 feet deep, right? So let's call this our water level. And we know that the volume of the cone should be 1/3 pi r squared times h, but we need to come up with a ratio here between the radius of 6 and the height of 12 with the radius here and the height of the water level. So it sure looks to me like that'd be 6/12 is equal to r over h, using similar triangles because they share this angle in common and they both have a right angle. So angle-angle similarity. So we just need to substitute in something here, put it in terms of one variable. We're asked about when the water is 3 feet deep, that'd be an h value, right? When h is 3. So it seems like it'd be best to solve for r, giving us r is equal to h over 2. And then plug that into our original volume equation. So now we'll have volume is 1/3 pi times h over 2 squared times h. Or volume is going to be pi h cubed over 12. So we'll take the derivative with respect to time, dv dt is equal to pi h squared over 4 dh dt. And now we'll just plug everything in to find what dh dt is. Now, dv dt was given to us in gallons per minute, and it's 10 gallons per minute, but that's 0.1337 cubic feet for 1 gallon. So our dv dt is going to be 1.337. So we have 1.337 is equal to pi times our height, which is 3 feet squared divided by 4 dh dt. And so we'll just take 1.337 multiplied by 4 and divide it by 9 pi. I'm not going to get out the calculator and do the arithmetic on it. dh dt is just going to be approximately equal to 0.189 feet per minute. So just solve that for dh dt there. All right, we got one problem left to go here. We've got a softball diamond that's in the shape of a square. The sides of the square are 60 feet long. We got a player that's running from second base to third base. So let's draw the baseball diamond. It's just a square. Ooh, that's a really bad square, but it doesn't really matter. The sides are 60 feet. Remember, this is doesn't look like it, but this is a square. We'll put our bases out there. So we got our player that's running from second base to third base, right? So second base is over here, right? This is home. We got first. We got second. We got third base. Player is running between second base and third base. He's somewhere over here. That makes a nice little right triangle with home plate because we want to know at what rate her distance from home plate is changing when she's 20 feet from third. Right, so this will be our x. This can be our y, which is going to be 60 because the distance between third and home is not changing. And this we'll call our z. So we can write this out as just x squared plus 60 squared equals z squared. And if you used y in there, that'd be fine. Eventually, you'd have a dy dt term, which would just be 0 because the rate of change between third base and home plate isn't changing. So when I take my derivative here, I really just get 2x dx dt is equal to 2z dz dt because the derivative of 60 squared, that's just a constant, so its derivative is 0. So now we just need to look in here and see what values we need to plug in. Well, x is her distance from third base, right? It says what rate is her distance from home plate changing when she is 20 feet from third. So our value for x should just be 20. And again, we'll cancel out the 2's also. Might as well cancel out the 2's. Right, so we got x is 20, and dx dt was given to us. She's running at 24 feet per second, right? But when we do that, dx dt, we need to be careful about that because she's running at 24 feet per second, but the value of x is getting smaller, which means that the rate of change of x is negative 24 because that distance is decreasing. So its rate of change must be negative. So we have 20 times negative 24 is equal to our z value, which we don't have yet. So we'll figure that out, times dz dt. So we got to figure out what that z value is. And we're looking for dz dt in the end. Well, to find z, we're just going to put in 20 for x into our Pythagorean theorem equation. Right, we'll have 20 squared plus 60 squared equals z squared. And, that's just going to be 400 plus 3600 equals z squared. That's going to give us z squared is equal to 4,000. Z will then be the square root of that. That's going to be 400 times 10 inside the square root, so it'll be 20 root 10. So our z value is 20 root 10. And so now we just, we can cancel out the 20s, and we're just going to get dz dt is equal to negative 24 over root 10, and this was in feet per second. And that is the end of this homework assignment, the Moore optimization and related rates homework.